In section 2, we are going to look at some reviewing of dividing polynomials and then look at a couple theorems to start looking at our main topic for this chapter, which is finding zeros for polynomial functions. So one of the kind of things we did when we divided polynomials in Algebra 2 or previous coursework is there were typically two ways we could do it. We could use what's called polynomial long division, and then there was its shortcut of synthetic division. Now, polynomial long division is just simply used when you want to divide two polynomials. So we're just going to use it to divide two polynomials. And it works very similar to the way you did division in grade school, where we do long division, where we say maybe 3 divided by 42. 3 goes into 4 one time with a 3. We subtract. We have a 1, bring down the 2. That goes in 4 times, 12, remainder of 0. So we're going to do a very similar thing with polynomial long division. And this remainder is actually very important. It's probably the most important thing that we'll talk about when we do our division. So our first example says a squared minus 2a minus 15 divided by a minus 5. So if I want to divide this, I will start by putting the divisor outside of the dividend. And the key thing to polynomial long division, as you recall, is all we're really looking at is the first term here and the first term here. That's really it. So we're going to divide those two. So we're going to take a squared divided by a, and this is, say, a to the first, so a squared divided by a is just a to the first, because we're just basically subtracting these exponents. So a squared divided by a is a, so I'll put an a on top. So the next part of this, as they call it, division algorithm, is to multiply that a to both of these values here. So a times a is a squared, a times negative 5 is negative 5a. So now the key part, and this is where people usually mix it up, is now just like in regular division, we're going to subtract. So we're going to subtract this polynomial. So a squared minus a squared will cancel out, and then you have minus 2a minus a negative 5. So negative 2a minus a negative 5a is going to be 3a, because of course the negative become a positive. And then I'll bring one value down, which is negative 15. And now I'm going to just basically do the same thing again. I'm going to look at the first term in each one. I'm going to look at the a and now the 3a. So I'm going to do 3a divided by a. A's cancel, so I just get 3. So my next term up here is 3. And then it continues. I'll take the 3 times both of those values. So that's 3a. 3 times negative 5 is negative 15. And now when I subtract, 3a minus 3a goes away. Negative 15 minus negative 15, which is plus 15. So there's no remainder. So whatever is remaining up here is our quotient. And so very important, we know our quotient. So what we've really just shown is we found what polynomial, in this case it's a plus 3, times our divisor a minus 5 is going to equal our dividend, which is a squared minus 2a minus 15. All right, let's look at another example. This one's, again, very similar. We just have a linear term in the bottom. So we have x plus 2 as our divisor, and we have x squared minus 5x plus 3 as our dividend. Now, none of these problems have had this yet, but I did want to mention that you have to make sure you have all your powers of x. So you have to have, if you start with a square, you have to have a first power and a constant. If not, you sometimes have to put what's called a placeholder, where we put 0. So we'll do division again. So I have x squared and x I'm dividing. So x squared divided by x is going to be just x, so that's going to go up here. I'm going to multiply it to the front, so x times x is x squared, x times 2 is 2x, and then I'm going to subtract those. So x squared minus x squared goes away. Negative 5x minus 2x is negative 7x. I'll then simply bring down the positive 3, and I'll go again. So I have the x, and now I have negative 7x. So I'll do negative 7x divided by x. These cancel, and that just gives me minus 7. So minus 7x and minus 14. The only difference in this one is we're going to put a remainder in this problem, because negative 7x minus negative 7x cancels out. 3 minus a negative 14 is 3 plus 14, which is 17. So this is our remainder. The way we generally write a remainder in a problem is I'll just say plus 17, which is the remainder, divided by x plus 2. Quite honestly, if our remainder is not 0, we're not going to really be too concerned about it in the future, but for now, that's how you'd formally write the quotient. Let's look at one more long division problem. This one's a little longer, but kind of has the same kind of principles here. So we have w plus 3 divided by 3w cubed. So I want to make sure every power is there. So there is a square power, and there is a first power, and there is a constant. So same idea. We'll take the 3w squared and divide it by w. I'm sorry, that's 3w cubed divided by w, which is 3w squared. I'll multiply that to both terms in the divisor, so that's 3w cubed plus 9w squared. And I'm going to subtract. So 3w squared, of course, cancel. 7w squared minus 9w squared is negative 2w squared. And then I'll bring down negative 4w. So we'll take negative 2w squared divided by w, which is negative 2w. Multiply it around. Negative 2w times w is negative 2w squared. Negative 2w times 3 is negative 6w. Subtract. Negative 2w squared minus negative 2w squared cancels. Negative 4w minus a negative 6w is like plus 6w. So that's going to be 2w. And then I'll bring down the positive 3. Last line, 2w. So you just keep doing this until you run out of terms to divide, essentially. That's going to be 2, so we'll put a 2 up here. Multiply by the front, 2w plus 6. We'll do our subtraction. 2w minus 2w cancels. 3 minus 6 is negative 3. So our quotient's 3w squared minus 2w plus 2 minus 3 over w plus 3. Now this is a fine process, but it is somewhat tedious. So a lot of times when we want to divide just by a binomial, we'll use a different type of division called synthetic division. Okay, let's look at a couple examples of synthetic division. So as I mentioned, synthetic division is when you're dividing a polynomial by a binomial. And that binomial has to look like something like x minus a. So you have to have some value after an x. So, for example, I could divide x squared minus 3x plus 2 divided by x plus 8. I could use that using synthetic division because I just have the binomial x and then some number. So synthetic division as a process, it'll look a little bizarre, but it actually is really quick. So what we do for synthetic division, let's divide this polynomial, is I am going to put a sideways L that looks something like this. Now I'm going to take my divisor, which in this case is x plus 1, and I'm going to find what makes that 0. So what value makes x plus 1 equal to 0? It's, of course, negative 1. Because that's the number after the minus sign. Because remember we said it had to be x minus some number. So technically this is x minus negative 1. So negative 1 is the number I put out here. On the inside, I'm going to take all the numbers in front of my terms. And I'm going to make sure that I include all the powers. So I'm going to put a 1 for the fifth power, a 1 for the fourth power, a 1 for the third power. Sorry, it's a negative 1 for the fourth power. 1 for the third power, negative 2 for the second power, 3 for the first power, and negative 6 for the last power. So we have the numbers on the outside for the bottom and the numbers on the inside for the top. Then the process is we'll first bring the first number down, which is 1. And then we'll multiply negative 1 times that number, and we'll put it right next to it. So negative 1 times negative 1 is negative 1. So that goes there. Then the process goes, we will add this column. So negative 1 and negative 1 is negative 2. And then the process continues. So negative 1 times negative 2 is 2. That goes there. 1 plus 2 is 3. Negative 1 times 3 is negative 3. Negative 2 and negative 3 is negative 5. Negative 1 times negative 5 is 5. 3 plus 5 is 8. Negative 1 times 8 is negative 8. Negative 8 plus negative 6 is negative 14. Now what I'm going to do is I'm going to put a little box around that last number. And here's why. I actually have just divided these two polynomials. This last box is giving me the remainder. And then the other numbers you see here are actually giving the rest of my quotient. And what I have here is, you see this started with a fifth degree. The highest power is 5. So 1 less power would be 4. So our quotient should be a fourth degree polynomial. So if you see these numbers, the first number goes in front of an x to the 4, because that's 1 less than what we started with. The next one, which is negative 2, goes in front of an x cubed. The next one goes in front of an x squared. The next one goes in front of an x. And then if we did it correct, you should end with a constant. And then, like I said, this last number is our remainder. So if I wanted to write it, it's negative 14 over x plus 1. So I obviously did that in a lot quicker method than I did the other ones. It's really fast to just do that division. Key things that typically people forget is to remember to start this with 1 less degree. So it was a 5, so I should start with a 4. Let's look at another example, and we will do a ton of examples because synthetic division is something we'll use basically every problem in this chapter. So we have negative half here, and then I'm going to put my numbers on the inside, so 12. And now you notice there's no x squared, so I'm going to put a 0. We've been talking about how that can happen. You got to make sure you account for all the powers. Since we started with a cube, we have to have a square, so we'll put it in there. So let's bring down the 12. Negative half times 12 is negative 6. 0 and negative 6 is negative 6. Negative half times negative 6 is positive 3. Negative 2 and 3 is going to be 1. Negative half times 1 is negative half. 5 plus a negative half, or 5 minus half, is going to be 4.5. Or just 9 halves, whatever you want to put as your remainder. So that's my remainder. So my final quotient is going to be 12x squared, because remember, it started with a cube, 1 less is squared, minus 6x plus 1, remainder is 9 halves. So we could write it as 9 halves over x plus 1 half. Something like that. So last thing we want to look at in this chapter is what's called using the remainder theorem. Now the remainder theorem is just a really quick way to get a remainder when you divide two polynomials. So essentially it does what synthetic division does, except it just finds the remainder. So the remainder theorem says this. It says the remainder of dividing f of x by x minus a is simply f of a. So what it's saying is instead of plugging everything in or dividing everything out, all I have to do is plug in this value for a into the function, and that value will be my remainder. So instead of actually having to divide, if you just want the remainder, all we have to do is just plug in to the function. So we'll look at an example where we do it both ways. Here's a polynomial, which is divided out by x plus 2. It says use the remainder theorem. So we're going to think of this is our function f of x, and we're going to think this is our x minus a. So minus a in this case is going to be negative 2, because it's minus negative 2 to get the plus. Remember, it's always the opposite. So the remainder should simply just be f of negative 2. So if I plug negative 2 into my polynomial, I should get the remainder. So that's negative 2 to the 4th minus 3 times negative 2 squared plus negative 2 minus 2. So if I plug this in correctly, I believe this equals 0. So I'm going to claim by the remainder theorem that this division has a remainder of 0, because the remainder theorem says whatever I plug in, it should give me that remainder. So to verify it, let's just quickly synthetically divide these two out. So that's a negative 2 on the outside, and then 1, 0, because there's no cube term, minus 3, 1, and minus 2. So if we've done everything correctly, this should turn out to be 0 as the remainder. Bring down 1. Negative 2 times 1 is negative 2. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is 4. Negative 3 plus 4 is 1. Negative 2 times 1 is negative 2. 1 and negative 2 is negative 1. Negative 2 times negative 1 is 2. And that's 0. So you can see these remainders match. They gave us the same value. Now, if I don't synthetically divide, I really don't know these numbers. All I really know is the remainder. But in a lot of cases, that's all we really need to know. So here is our last example, and this kind of goes and talks about ways to find zeros of a polynomial function, because that's something we talked about being pretty important in our last chapter. Remember, zeros are just values that I plug in and it makes the function equal 0. So when this problem says I want to find the zeros, I'm really trying to figure out this equation, 0 equals 6x cubed minus 7x squared plus 1. But it tells me I know one of the zeros. Okay? Well, since I know one of the zeros, if it's a 0, it has to be plug in to equal 0. That means it has to have a remainder of 0. Because remember, the remainder theorem says whatever you get when you plug in is what you should get on a remainder when you divide out. So since this gave me a remainder of 0, and I know one of these is 0, I can divide that out. So my 0 is at 1. It says I want to find the zeros if I have 1 0 at x minus 1. So if I divide out 1 from my polynomial, 6, negative 7, 0, because there's no first term, and 1, I get 6. 1 times 6 is 6. Negative 7 plus 6 is negative 1. 1 times negative 1 is negative 1. That's negative 1. That's negative 1. That's 0. So we know 1, 0 is 1, and now I get this remaining polynomial, which is 6x squared minus x minus 1. So if I want to know what the zeros of this polynomial are, I can simply set this equal to 0 as well. So I knew 1, I divided it out, and this polynomial here will contain my other zeros. This contains other zeros if they exist. This could have no zeros that are real, but it might. So now we have a quadratic, you'll notice. So I divided out the 1 because I knew it had a remainder of 0. And so I get this polynomial I can now solve. Now, this is like stuff we did in section 1. So you can use quadratic formula. You can factor whatever you want. I'm simply just going to factor this to find my other two ones. Now, in all this, you could have also graphed this as well. You could have graphed it and saw where the zeros were. But just to do a little more algebraically. So if I think this factors is 3x and 2x. minus 1 and plus 1, because there's our negative 3 and plus 2. So that's going to give me x of negative 1/3 and x of 1/2. So our zeros are going to be 1, because that was given, negative 1/3 and 1/2. And remember, since zeros are just where it crosses the x-axis, if you graph, these should be my 3x intercepts as well. So anytime you're asked a problem about the zeros or finding real zeros, you're really just looking for x-intercepts. I did it more algebraically here, and we're going to continue to do that, but that's always a great way to check your work.